Hello, I'm Patrick O'Shaughnessy from the University of Iowa. This is Module 6 of the grouping of statistical courses called Statistical Methods for Analyzing Data Obtained in the Lab or Field. This module will cover experimental design techniques. It is recommended that you review modules 2, 3, and 4 prior to this module. And then ultimately we're going to move from this module into module 7 on the analysis of variance and the techniques associated with that, which all are grouped together and intertwined in terms of the knowledge base associated with them. So again, highly recommended that you review 2, 3, and 4 first before this one, and then this one before the next one. Then here's the module map that includes this 14th module. You can see it's part of a series of multi-sample test types, and you should review certainly module 13 before this one. And at the end of module 13, it talked about a typical type of sampling method, which is to completely randomize your sampling, and then this module starts from there. Okay, now this completely randomized design is exactly what it sounds like. And this is a classical experiment where you're trying to randomize things as much as possible. We do that to avoid bias. There's perhaps the sequence of events. It's impossible to get beyond time. It takes time to do one experiment and then do another one and then do another one. And is there some sort of a bias that's incurred by this sequence that you may apply? So with a completely randomized design, you want to compare a number of treatments that are going to be associated with the number of factors and their number of levels, right, as already described, which will tell you how many treatment combinations you have, and that you have the ability to apply these treatments randomly to these experimental units, which are the situation that will give you the number you're looking for, and that each experimental unit has the same chance, therefore, of receiving any one of these treatments. And all of this, again, is based on the idea that your experiment is such that you have the control over the process to be able to literally do this and assign these treatments to experimental units, and this assigning process is random. And we can go one step further, and a balanced design is what they refer to when you have the same sample size for each, or excuse me, the same number of observations for each treatment combination. So getting back to this example that we talked about in the previous module of cutting speed versus mortar type, again, this is 2 factors, one at 2 levels and one at 3 levels, which causes us to have 6 treatment processes. But within each one of those, we're going to have an n of 3. So we're going to repeat it 3 times. And you can see by just the way these reps are enumerated here, rep 1, and then rep 9, and then rep 14. So this is the randomization that in the process of actually doing this, we're going to set up the experiment at 2,000 and hard and do rep 1. Then we're going to jump to 3,000 and hard and do rep 2. And then we're going to jump down here. So we're randomizing which one of these treatment combinations gets done at any given time. Again, all for the purpose of minimizing bias that may be associated with going through these sequentially in increasing order of cutting speed, for example, that may influence the results somehow. Okay, so this completely randomized design, again, let's get back to this concept of used to compare P treatments in which the treatments are randomly assigned to n experimental units. Okay, what does that mean? Well, for example, we want to know how long it takes to assemble a product by workers using 3 different fabrication processes, and they want to know probably maybe which one's the fastest. And they're going to use a balanced, completely randomized design. And that's decided based on their power estimates or whatever to have enough power, but they're going to have 10 workers for each process. So that's also going to balance it out. Now, in order to have this as a completely randomized design, we need to randomly assign the 3 treatments. This is a 1-factor experiment called, the factor is the fabrication process. And there are 3 levels. Fabrication type number 1, fabrication type number 2, fabrication type number 3. So that's why there's 3 treatments. Treatments equals the levels. And we want to randomly assign to the 30 workers to result in 10 workers for each process. Okay, how are we going to go about doing that? Okay, so again, let's just review here some of the terminology. What's the response variable? It's going to be the measurement of assembly time. Okay, that's our Y. How many factors? 1, as we just discussed. How many levels? 3. 3 different fabrication processes. Treatments. There's only 1 factor, so again, the levels equal the treatments equals 3. How many total samples? We have 3 levels times 10 workers, 30 workers. Okay, so now we know. We've got to go out and get 30 workers, and we have to randomly assign the 30 to the 3 different fabrication processes. So here's one technique. You got worker 1 through 30, as shown there. And then you cut out little pieces of paper with the number 1 on them, throw them in a hat, 10 of them. Then you cut out 10 little pieces of paper with the number 2, and the same thing for number 3. Then you shuffle them all around, and you pull out a 2, and so you assign that to worker number 1. Then the next thing you pull out is a 1, you assign it to 2, etc. So now I know with that technique that I will have 10 1s and 10 2s and 10 3s, and they'll be randomly assigned to the 30 workers. And we can then kind of recombine our choices by fabrication method to end up with this result here, which would be, again, an example of a completely randomized design. It could happen even if you had 100 workers. Some would get, in that case, 70 of them would just have a 0 on them, meaning they aren't going to be part of the study. But you need at least 30, obviously, for this experiment. Okay, so that simple random sampling, we're applying that to a completely randomized design. The other main type of design I want to discuss, because it comes up quite a bit, is called a randomized block design. So you, just by way of the experiment, you may have a reason to know why some of the treatments should be separated into blocks containing similar values, which will help to lower the variance between them. It's called a noise reduction method. And what all that means is we'll discuss here in a minute. But first of all, it's good to note that, again, if you've seen the previous module, you'll say, oh, that's kind of what we did with a paired t-test, right? The experimental runs cannot be made under homogeneous conditions because there are differences in time, place, etc. We can't just randomly associate a bunch of workers, for example, as we just did. The type of experiment, unfortunately, for example, happens to occur on day 1, day 2, day 3, day 4, and day 5, and each one of those days may have different weather conditions, for example. And so when I'm comparing between 2 sites on those 5 days, I don't want all these different weather conditions between the 5 days to kind of add to the noise that keeps me from distinguishing between the 2 sites. We are separating the sites into blocks so that we can reduce the noise between the blocks. Okay. Sometimes they call this, when a block, this nuisance factor. Okay, different days, we don't care about different days, we just care about different sites. So, okay, more on the randomized block design. As state it as concisely as possible, but admittedly a bit confusing, you're going to compare P treatments. In this case, 3 different fabrication methods. So there's 3, P is 3, and involves B blocks. In this case, 10 workers, each containing P experimental units. And they are the P treatments are randomly assigned to the experimental units within each block. So, for example, we had this previous experiment where we chose 30 different workers, and we put 10 of them associated with fabrication method number 1, 10 for 2, 10 for 3. Now you may be wondering, it's possible that the randomization didn't work so well for us, and actually the 10 workers associated or assigned to fabrication number 1 happen to be the slowest workers in the plant anyway. So now the result is going to be that fabrication method number 1 is a slower method than 2 or 3, but it's only because of the slow workers we assigned to them. So again, see, we don't care about workers or the difference between them. We care about the fabrication method. So one other approach, as shown here in the table, is you assign the same worker to all 3 fabrication methods and then compare between fabrication methods. Right, now you've taken out this issue of differences between workers. Okay. So that is what we mean by this kind of noise or this nuisance effect, or the workers and the difference between them, because all I care about is fabrication method. And then you can see that in terms of randomly assigning the experimental units just means that in every case, well, first of all, yes, there is each treatment, which is the fabrication methods, appears only once per block, and the workers are the block. We're blocking by worker, the nuisance factor. And then we're going to assign them randomly. So worker number 1 is going to do fabrication number 2 first, then 3, then 1. And then 2 is going to do 1, 2, 3, etc. That's what they mean by randomly assign to the experimental units. Okay, so now we've seen 2 kind of most classic approaches to experimental designs. You either do it as a completely random method if possible, and or you're going to apply some sort of a blocking technique, which again is completely analogous to the paired t-test. Now in general, these approaches can be called factorial designs because we've been talking about these factors, right? They require careful selection of the combination of the factor levels in the experiment, and they're used to determine the relationship between a response of interest, whatever that Y is, and the factors that influence that response. So in engineering, they may be chosen because they know that the system that they're working on, trying to design, is influenced by several factors, and they want to do an experiment to determine which factors influence it the most, and or at what levels do we want to put those factors to optimize the system. So again, these factorial designs also typically involve more than one factors, but they don't necessarily have to. They can be a one-factor experiment as well. So let's do one more example here. We have a researcher. He's interested in the effect of humidity on the ability of a respirator to capture dust particles. They know that humidity may have an effect on this capture ability. So they're just knowing that, then the researcher now has to decide, okay, if I need at least 2 levels of humidity if I want to make this comparison. And also, now they could stop right there. They have a respirator that they know about. They're going to give it 2 levels of humidity, compare them, and see which one has a higher mean efficiency than the other in terms of humidity levels. What kind of test would you apply in that kind of scenario? A two-sample t-test. That's what it is. However, there are more than one respirator types out there, and this researcher is also interested in maybe this effect will have an effect on one respirator, but maybe not on the other. So they are going to call respirator as well a factor, and it has to have at least two levels. So that's what he does. Respirator type 1 and type 2. And he has chosen humidity levels of 35% and 95%. And the response variable, again, is this capture efficiency in a percentage. Okay, now it's a matter of what are we going to do? How are we going to set this up as an experiment? How should the researchers select treatments for the experiment? First of all, these are the combinations of levels, right, that we've seen already. So if you're just kind of going at it in a quasi-logical way, you might consider this kind of the one-at-a-time approach. So what are you going to do? You're going to, one independent variable, one of the factors, is varied while the other is held constant. And then you can repeat for each of the independent variables. Hold one constant, change the other two. Then hold the other one constant, change the other two. Okay. So for example here, we're going to call this RH is x2, hold it constant at 35%, and observe what happens when you apply 35% to respirator type 1 and respirator type 2. Then you're going to kind of flip that around. You're going to keep x1 constant at type 1 and observe the response at 35% and 95%. And then maybe just to make sure, you're going to repeat this whole process again to get two values for each of these treatments that you have come up with. Sounds good and logical? Why not? Sounds like we caught everything covered. But method 2 is that you carry out 4 experiments that include all possible combinations of respirator type and RH level. What wasn't covered before we held humidity at 35% and then looked at the 2 respirator types. Then we chose respirator 1 and looked at it in terms of 2 humidity levels. You see what happened in that process of just kind of doing it intuitively is we actually missed an entire possible combination, which is respirator 2 at the high humidity level. Just didn't factor into the experiment, as versus making sure that it does. And how can you make that sure? Draw out the table. 2 rows times 2 columns gives me 4 possible treatment combinations. I have to make sure that all 4 are part of the experiment. So that's the selecting all treatments approach, which gives and ends up giving more information. So you can say, well, both give 2 estimates of the difference between the mean response when x1 varies, when x2 is held constant. Okay. X2 is held constant. We go this way, we've got that, and we've got this approach. You can see we think we have everything we need. The problem here is, what if the difference between the mean response of y when x1 varies depends on which x2 is fixed? This is what is known as interaction. It means that when you adjust x1, it changes the way x2 affects the response. That makes sense. The level of x1 will change the way x2 affects the response. The level of x1 should have no effect on the way x2 affects the response. That is x2, you hold x1 constant, right? It's not doing anything. And now I change x2 and see how it affects the response. Then I change x1 again to its high level, say, and all of a sudden the way x2 affects the response is kind of different than the way it did before. in a sense, as we'll see, it has a different slope. It affects the response differently. That is interaction. You cannot get at interaction with the one-at-a-time approach. You have to have all 4 treatment combinations to see whether or not your factors interact with each other. And if they do, that really has a big effect on your ability to distinguish whether X2 affects the response, meaning the different levels of X2 affect the response. And we'll see this in the next lecture on ANOVA analysis. So we have to consider interaction. So finally, these factorial designs are methods for selecting the treatments to be included in an experiment, and you should definitely think along these lines if you are capable of it, meaning your system is capable of allowing you to choose an X and choose sample sizes, etc., that fall into this type of design process using either a completely randomized design or a random block design. And to be certain that you have a complete factorial design, which means that you have all possible factor level combinations covered as part of the treatments that you are going to apply. And now just to get into a little bit of math here, just to introduce this concept, although we're going to try to get around it as best we can in the next module on ANOVA. You can see here that we can actually enumerate the, say, a 2-factor experiment in terms of what are called the main effects. And now we have an enhancement of the linear regression equation that we saw in module 5 with, instead of just one x1, we have a beta 2 x2. But there's also a possibility of putting in what's called the interaction term. And interestingly, you see it's x1 times x2 will help to incorporate this concept of interaction. And then, of course, epsilon is the kind of the random effect aspect of things. Now, in the next module on ANOVA, we will try to see whether or not x1 is significant and x2 is significant, and hoping, in a sense, that the interaction is not significant. That is, in this case, it's whether or not the beta 1 slope is significantly different from 0. Yes, then x1 is definitely having an influence on y. Same thing with beta 2, if it's significant. Those are kind of the things we're looking at. If beta 3 is significant, then that has a real consequence in how we can interpret these, because they're interacting with each other, and sometimes in some unknown way. So if they're interacting with each other, how can we say explicitly that x1 by itself is affecting y, x2 by itself is affecting y? So that's the importance of knowing the interaction term. And with that, we'll conclude with this module and move on to ANOVA analysis in the next one.